Hey guys, welcome back to 24/7 Chemistry. Today we'll be doing acids and bases. So we got three different, buffers and Henderson-Hasselbalch equation, which relate to acids and bases. So let's just jump right into it. So the first thing we're going to do is just identify the pH and buffer capacity of a solution. And to do this, well, first we're given what's going on here is we have two solutions. Let's say this is the sodium acetate. We'll just do ASC for short. And then this one is the acetic acid. We'll do HSC. Okay, so we pour them together to make a new solution. So this one is going to have 50 ml, and this one is going to have 30 ml. And so why is this important? It's important because, well, you would think for this, first of all, whenever you hear buffers, the first thing you should be thinking of is the Henderson-Hasselbalch equation. You could use an ice table, but it's a lot longer and a lot complicated, more complicated than if you were to use just a simple equation. But before that, we need two things. We need the pKa and the concentrations of the conjugate base, which is sodium acetate, and the acid, which is acetic acid. Um, and while we do have concentrations here, they're not the true concentrations. They're the concentrations before we mixed the solution together. So when you mix the solution together, you have the two solutions together, you have a new solution, and therefore a new concentration for both, right? And here's a little surprise. You could just find the moles and plug those into Henderson-Hasselbalch because, well, I'll explain that in a bit. But that's as simple as it gets. And what is buffer capacity? I'll explain that in a bit as well. So all we have to do is find a new concentration and find the pKa. Well, here's a little tip for you guys. P to anything like pH, pOH is just the negative log of that thing. So in this case, pKa is the negative log of the Ka. And so we can calculate that. pKa equals negative log of 1.8 times 10 to the negative 5. I'm writing a bit big. And that's just going to equal 4.74. And we're going to keep that to 2 sig figs. And if you guys don't know how to do sig figs for log rules, you basically just show you guys in a second. What you do is, so the Ka is reported in two significant figures. And so that significant figures amount is gonna be reflective of after the decimal point. I don't know if that makes sense. Basically, this is significant always, but your true significance is determined by what's after the decimal point. So in this case, 7.4 is 2. But 4.74 all in total for log rules is still two significant figures because we count it after the decimal point. Okay, so we found that, and what we're gonna do is now we're gonna find the moles. Okay, so starting with sodium acetate, of course, molarity equals moles over liters of solution. In this case, we're talking about the starting solution because that's what it gives it as. And the top is moles of solute, right? Which means we need the milliliters turned into liters. And that you're just gonna divide by 1,000. I think at this level, you guys should be pretty comfortable with that. Let me know if you want a video on a tutorial on how to do that kind of stuff. Um, there's a little hack I have. But anyway, so we're going to do 0.03. We'll start with acetic acid. Times that by 0.100. And that's going to equal. I should really include my units for you guys. That's going to equal 0.003 moles. Yep. And yeah, it should be in 2 sig figs. So 30 moles. So we have that part now. And so now if we go down, now it's going to be 50 mils. So 50 ml. Or that should be 0.050 liters times 0.255, and this one's for sodium acetate. And that is going to equal 0.01275 moles of sodium acetate. Okay? And so we have those, and just like I said, well, to find the concentration, we would just add the two liters because, well, we mix the two solutions. When we mix them together, the volumes are additive. So that would just be 0.050 liters over, sorry, not over, we're so plus 0.030 liters equals 80. Well, I'll keep it the same unit. 0.080 liters, right? So, and then we would just divide because molarity is just moles over liters of solution. But since we're going to be dividing these two by the same things, they cancel out either way. So we actually can just skip a step and we don't have to divide them. We can just plug in the moles straight into the Henderson-Hasselbalch equation, which is going to be pH, and remember that's what we're trying to find, equals the pKa, which is 4.74, plus the log of the concentration, in this case it's going to be the moles, of the conjugate base, which is sodium acetate, 0.01275, over the acetic acid moles, 0.003. And we're going to get a pH. I'm not really focused on sig figs right now, by the way, even though I mentioned it earlier. But the pH is going to be 5.37. And so what's the buffer capacity? Well, what is buffer capacity? Buffer capacity is basically how much a buffer solution can handle before the pH just starts to increase or decrease drastically. And this is usually a range. So we found this pH, and the range is plus or minus 1 from the pH that we found that the solution is at. So in this case, 5.37 minus 1 would be 4.37. So that's minus 1. And then 5.37 plus 1 would be 6.37. And that's your buffer capacity. Okay. And I should have mentioned this earlier. I'm still kind of getting the hang of, filming and what have you. But I wanted to go in depth as to what a buffer is. There's not really much to get in depth with, but it's basically a solution that can resist changes in pH, and the solution contains an acid in its conjugate base. Every time you see an acid in its conjugate base, that's a buffer solution. And this is important because one very vital application is talking in terms of physiological pH. So our bodies are filled with buffers, and we need them so that our blood doesn't become too acidic or too alkaline, aka basic. Because if that would happen, we would get something called alkalosis or something like that, and acidosis. Um, and for example, when you hyperventilate, your body becomes a little bit acidic, and that's why you're at risk to pass out. So that's why buffers are important in the real world. And just for many other reasons and that don't relate to biological systems. Um, so let's move on to question two. Oops. Okay. In this case, well, we're doing kind of something similar. We don't need to find the buffer capacity, but we do need to find the pH. And what is happening is we're actually adding acid. So there's a really interesting thing going on. Well, already in our system, okay, we already have conjugate base, in this case, ascorbate, and conjugate acid. Or not conjugate acid, just acid. In this case, ascorbic acid, which is found in vitamin C. When you add HCl, well, what does HCl break up into? It's a strong acid, so it breaks up completely. And it breaks up into H plus and Cl minus. Why is this important? Well, in this case, the Cl minus isn't important to us, right? So we can just forget about that guy. But basically, when we add HCl to the solution, it breaks up into H plus and Cl minus completely because it's a strong acid. And this H plus is going to react. Well, it's not going to react with another acid. Acids don't react with acids. It's going to react with base, right? So as you're adding HCl, you're actually adding H plus. When you add H plus, it's going to react to the conjugate base. And so what's going to happen is that, well, I'm going to write it down here. H plus plus ascorbate, that just makes ascorbic acid. And why is this important? Well, the more these two guys react, the less ascorbate you'll have because you're using it up. And the more ascorbate you use, the more ascorbic acid you'll make. So basically, the more HCl you add, the lower the concentration of ascorbate becomes. And conversely, the higher the concentration of ascorbic acid becomes because it's reacting. And as a result, your pH will be lower than before you added the acid. And just conceptually, that should make sense, right? So how do we do this mathematically? First, we're going to convert everything to moles because when I gave you this problem, it's kind of like in problem one. We reported it in uh, the volume and concentration of the two separate solutions. So first, we got to find the moles, and we can start with ascorbic acid. I'll try to do this a little more organized for you guys. Okay, and that's just going to be your 22 mils. I converted that to liters real quick. Okay, times 0.0125 molarity, and that's going to equal 0.00275. Okay. And so same thing. We're going to do the exact same thing with ascorbate. So that's going to be 0.033 liters times 0.600 molarity equals. And that is going to equal 0.0198 moles. Okay. And so we actually have to do the same with HCl. And the reason is because however many moles of HCl are uh, are there is going to be exactly how much that will react. And sometimes you'll get examples where there's excess HCl. So there's, when you add all the HCl, all the ascorbate reacts, and all you have is ascorbic acid. In this case, all we have not excess of HCl, it's all going to be used up, right? So however much moles of HCl we added is going to be how much moles of HCl that will react with ascorbic acid or ascorbate. Um, and so as a result, that's how much ascorbate will be used, and that's how many moles will be used. And so we can just subtract the moles of HCl from the moles of ascorbate, because like I said, all of the HCl will react with the ascorbate. And so that's how much ascorbate that you lost. Um, and conversely, however much ascorbate you lost is however much ascorbic acid you gained. So however much HCl you added is how much ascorbic acid you gained. So you're going to add the moles of HCl from with the moles of ascorbic acid, but you're going to subtract them from ascorbate. But first, let's find the moles of HCl. So we got 0.013 liters times 0.0955 molarity, and that's going to equal 0.01242 moles. Okay, so now I'm just going to do mathematically what I just talked about. We're going to subtract this and this because that's how much we used from ascorbate. The amount of HCl is how much, the moles of HCl is how much we used. So let's do just that, 0.0198 moles minus 0.01242. We're not really focused on sig figs right now. And that is going to be 0.01508 moles of ascorbate. Okay, so at the same time, we're going to do 0.002750. This is the moles of the ascorbic acid plus moles of HCl added, 0.01242. And that's going to equal, oops, this is actually, whoopsie, okay. I think I have a little bit of a, yeah, I might have made a little bit of a mistake. This number is not correct. Sorry, guys. Um, yeah, so it's actually going to be 0.01856. And That's moles of ascorbate. Okay, and then for moles of ascorbic acid, that's going to be, after we added them, 0.001508. Yep, that should be right now. Did I do my math right here? I might have. Interesting. I think I might have done my math wrong here. Um, I'll just do it real quick in my head. Well, I'll just do it on my handy dandy calculator. Yeah. All right. So this should actually be 0.00399 moles H ascorbate, uh, or ascorbic acid. All right. So once you do this, well, we also have to find the Ka. And we're going to do the same thing we did before, negative log. We need to find the pKa, that is. We got a negative log of the Ka, 7.9. Going to do that real quick. Times 10 to the negative 5. And that's going to equal 4.10. So once we've done all of this, we're going to plug everything into the Henderson-Hasselbalch equation. And like I said, we do not need to convert this to molarity because we're going to be dividing by the same thing, so it's going to cancel out anyway. All right? So, Henderson-Hasselbalch equation. pH equals pKa, which is 4.10, plus log of the concentration of ascorbate, which is the conjugate base. In this case, we're going to do moles because I've explained many times why we can. Moles. Okay, and that's going to be over 0.39, oops, 0.003992 moles of the acid, in this case, the ascorbic acid. I actually need to calculate that because I got the previous calculations wrong. And that's going to be 4.76. That can't be right. We added acid. Why is the P? Oh, wait. Nope, it's definitely right. Okay. 4.77 actually. And that should be your answer. All right. Great. So now on to number 3, which is a lot simpler than you guys might think. And by the way, actually, I'll mention this at the end of the video. Just about your guys' practice problem that I'll be posting. I'll mention that at the end of the video, though. All right, on to number 3. We're just finding the mass of fluoride. Fluoride being F minus, right? So, it's basically asking how much fluoride F minus or conjugate base we would need to add to hydrofluoric acid, which is a weak acid, to get a specific pH. So this seems really complicated, right? And by the way, it's pKa. I don't think it's actually, yeah, no, it's the right one. I thought I just made it up, but this seems a lot more complicated than you might think, right? We have the handy dandy Henderson-Hasselbalch equation to help us out. And so it's almost like it's plug and chug. So what we will be doing is we're just going to plug everything into that equation. Well, we have pH. I gave it to you guys. 3.600 equals. I gave you the pKa as well. I didn't make you calculate it because it's kind of getting old at this point. Plus log of, let's see. Well, we want the concentration of F minus, right? We don't have that yet. That's what we're trying to find in a way. Why? Because it's the only way for us to get to grams. Well, concentration has moles over liters. If we can get that rid of that liters, we'll have moles. And moles we can just go to grams, right? So that's kind of our goal here. That's our vision. And well, we have everything else though, as I mentioned. 0.878 m. So basically, here's a little tip. Whatever you punch into this log here is what you'll get out. So in this case, I put in molarity. So that's what this F minus is going to come out as, right? If we put in moles, like let's say if we multiply 396 milliliters by 0.878 molarity, we'll get out moles, right? And this is the more correct way, I would say, to do it. I'm unsure if you'll get the right answer. I think just conceptually thinking about it, if you were to, get this number into moles first and then isolate F minus, you'll be fine. I'm unsure of that, but you guys can test it out. But just remember that if you convert it to moles first, your concentration of F minus will be moles as well. Okay, so we want to isolate F minus. That's kind of our star here. And there's an easy way to start, and that's just subtracting 3.180 by both sides. 3.180, and that's just going to be 0.420 equals log of F minus over 0.878. Okay, so now how do we get rid of this log? The log is like glue, it's like the package. We got to get rid of the package. We got to open that box before we can get inside. So before we can just divide F minus, we got to get rid of that log. We got to open that box. So how do we do that? Well, the opposite of a log is 10 to the whatever this thing is equal to, right? So we just say like raise it to the 10. So whatever we do on one side though, we would have to do to the other. So basically, we would just raise both sides to the 10. And what would that look like? 10 to the 0.420, right? That number came from this, equals, I need to write this small, 10 to the log of F minus over 0.878 m. And this looks weird, I know. 10, so it's basically 10 to the this whole mess, right? And that actually just cancels it out. So these cancel out. So what you're left with is whatever's in that log, which is this stuff, right? So what we'll actually have, and 10 to the point for 20 is just a number. It's like saying 10 squared or 10 to the 1/2, right? Equals F minus over 0.878 molarity. And so now the math is simple. We're just multiplying 0.878 on both sides. That cancels out. Do that on both sides. And what you guys will find is that the concentration of F minus equals, it's pretty concentrated, 2.309 molar, right? Well, we have this in molarity. We want it in grams. How do we do that? Well, we're given a concentration of the solution, right? It's 396 milliliters. So if we break up molarity, remember guys, this is moles over 1 liter, or just liters, we can cancel it out to just get moles by multiplying by that volume, 396 liters. I just converted that in my head. I just divided that by 1,000. And what we'll get is that would equal 0.8522 moles of F minus. So now all we got to do is multiply that by the molar mass of fluorine. What's the molar mass of fluorine? It would be 19.00. So times that by 19.00. And you guys will get about 19.00 grams per mole. And so the amount of fluorine in grams that you have to add is about 7.0 grams to reach a pH of 3.6. And so about the practice problem, I'm actually for you guys to do. It's like a challenge problem. It mixes questions three, a 1, 2, 3. So and then I'm gonna post like kind of vague instructions that will guide your thinking. I'll post the answers to that as well. But that's gonna be in the description. So look out in the description and yeah, you can comment if you guys have any questions, but thank you for tuning in. I hope this helped, and as always, have fun with chemistry. That's the goal in life, to do chemistry 24/7. All right. Thank you guys again.